All right, how about now? Yeah, okay, great. So my name's Kevin. I'm a software engineer at NVIDIA. I'm really excited to be here. This is my second UGM if you count North America in April. Saw some familiar faces from there, which I'm really excited about. So I'm going to talk with you today about a couple of performance improvements that we've been trying to make to RDKit functionality. Some of these we've bundled into a library of GPU utilities, which we're calling NVMolkit. Some of them we are upstreaming CPU improvements directly to the RDKit code base. And the feasibility of putting things on the GPU versus the feasibility of improving RDKit in place kind of depends which functionality goes where. So I'm on the BioNeMo team at NVIDIA. We're a group of researchers and engineers who are trying to improve drug discovery, make it faster, make it better on NVIDIA graphics cards, and general improvements. We do that through a variety of libraries and services. Some of them are open source, like the BioNeMo framework. Some of them closed source, but freely available, like cuEquivariance, which tries to accelerate machine learning force fields that use equivariant models. And we do things with featurization for ChemProp with Quick Mole Maker, and we have some research efforts, and I'll have links for all of these at the end. Just real quick, the people who contributed today, myself, my manager, Sai, Eva is the other full-time employee working on this, and then we've had contributions from other people within our company, CUDA kernels, and oversight. So I've gotten some double takes about why NVIDIA is here and why we're working with the RDKit. And it's because RDKit is central to so many bio workflows and drug discovery workflows. It's a great tool, and I've loved working with the code base myself. It's been great. There are some RDKit endpoints that can be bottlenecks, either in their own right for high throughput workloads, or as a pre-processing step or a featurization step if you want to use molecules as starting points for training models or for inference. So today I'm going to go over NVMolkit, what it is, what it looks like briefly, just a primer on what to expect from GPU programming. I know it's a diverse audience of users and developers, so it's not going to be technical. And then I'm going to go over 3 of the RDKit functions, which we've started to accelerate on the GPU and have gotten some decent results on. And then I'll briefly go over the CPU stuff we've been doing with the RDKit main code base. So NVMolkit is a C++ library with CUDA. It links to RDKit at the C++ level. We use the same Python binding code as RDKit, and that lets us take Python data structures like an ROML or RDML and pass that directly to our C++ layer to minimize overhead. This library is open source under the Apache license. We released it earlier this week. The link is here and at the end. Our general philosophy is to try to match RDKit APIs as much as possible. So if RDKit has a function, we try to have a similar function. The exception there is when we're doing GPU programming, we often need to do things in batch in order to take best advantage of our hardware resources. And so often what you'll find is where an RDKit API will take in a molecule, ours will take in a list of molecules and do the operation over all the molecules at the same time. And that applies to a couple different aspects. So the hardware that we work on has a lot of parallel compute capability, which, as I said, means we need to run things in batch. If you try to process a molecule for something like fingerprints one at a time, you won't see any speed up over CPUs. You need to be doing a bunch of them at a time, transferring that data to the GPU, doing the compute, and sometimes transferring it back. These things are really good at high density, high compute density problems. So things that you're crunching a lot of numbers, you're uploading some floating point numbers and doing matrix multiplies on them, or something else that has a high ratio of compute needs versus memory needs. For matrix multiplies specifically, we've got specialized hardware called tensor cores, which can do further accelerations. These there's some exceptions, but they're typically limited to reduced precision, which is why they're super useful for ML models. It can be a little bit tough to get them working for general scientific programming, but we've managed it in one case here. We don't like code divergence. You don't like it in performance CPU work either, but it's a bigger problem, even than the CPU on the GPU, because a lot of our cores on the GPU, the multi-threading, some of them will sit idle if there's divergence. But if you can get your GPU saturated with compute, and if you've got the right data types and the right memory accesses, you can get some really absurd speedups. So in the specific case of 16-bit floating point on an H100, you can get a petaflop. So I think that's a quadrillion operations done per second. A more normal case, like what you'd see in molecular dynamics simulations, is using this single precision compute throughput, which can still get you 60 or 7 teraflops. So we're still in the trillions of operations per second, still a couple orders of magnitude better than CPUs. It can be hard to hit those theoretical values, but it's what we strive for. Okay, so the first thing I'm going to talk about is accelerating batch Tanimoto similarity. The and friends, as we've also done cosine similarity. I'm not going to talk about it here for simplicity, but we can also do things like dice similarity that hasn't been implemented yet, but it's within our capabilities. So most people here know what Tanimoto similarity is, but if you have a binary bit vector of features such as from fingerprints, from Morgan fingerprints that represent chemical aspects of molecules, you want to compare two molecules. The Tanimoto similarity is the union of the bits, so the bits that are common summed up over the summed up bits of molecule 1 plus summed up bits of molecule 2 minus the union. Now, I have a confession to make. When I came in here yesterday, I had just grabbed a random equation from the internet and didn't think I had to cite it. But then during Greg's talk, he got called out for having a Wikipedia link to attribute a picture of a bus. And then when I opened Discord, I saw 20 posts on the Smalltalk channel going through a deep dive of Tanimoto similarity, the various forms of its equations, and who should it be attributed to. So thank you to everybody who provided references for me here, going back between 2015, 1998, and then Andrew went all the way back to 1950, and then finally found the earliest one that we could find from 1920. So whoever called out Greg yesterday, this is your reference for Tanimoto similarity. So as I mentioned, to take advantage of GPU resources, we need to do things in batch. So in this case, the kind of use cases we're targeting are N molecules against M molecules, and the N and M can be the same. So one example of this is if you're trying to do some clustering and you want to use similarity as a metric, you would do self against self, N by N similarity matrix. But the other application is if you want to query a database, say you've got like 100 query molecules and you're trying to find hits against a database of millions or billions, you can use similarity this way. There are more sophisticated techniques, and I think some people in the audience here, write software to do that. But we know of several groups who are doing the brute force method, who are hoping to make this a bit faster. An N by M similarity problem is it's kind of an outer product. You end up with an N squared matrix. So it's not a matrix multiply, but because these bit vectors are 512 bits, 1024 bits, we can treat some of the memory patterns the way we do with matrix multiplies, which are pretty well optimized on the GPU, by taking in tiles at a time and reusing memory. And then one of my colleagues was actually able to kind of hack into the tensor core code by writing direct GPU assembly to allow us to do some of the bitwise operations on these tensor cores and accelerate them further. This is analogous to a matrix multiply, but instead of a multiply operation, it's an and or an or across the bits. And then instead of accumulating with a sum, you're accumulating with a population count, which is what we need for Tanimoto similarity. So I was looking for implementations of similarity to compare against. This is a 16,000 by 16,000 matrix of 1024-bit tandem modus calculations. So that's over 200 million pairs. And on the y-axis, we have the throughput in terms of comparisons per second that we can make between fingerprints. And so the RDKit's actually pretty robust already. You can do 10 million fingerprints at a time. On this data set size, I think that took like 10 or 20 seconds to get through. FPSIM2 is another library that does fingerprinting and databasing, which I use their CuPy backend because it's faster. It's not the fairest comparison because they're not set up for batches the way we are, but it's still pretty good performance. Yesterday, I saw the scikit fingerprints poster, and I talked to Jakob, and I got the benchmark for the scikit fingerprint program, which also has pretty compelling performance. And then ChemFP, Andrew, the person who tracked down the tandem modus similarity references, is the author, I believe. And it seems to be the state of the art on the CPU with the throughput of over 100 million pairs per second, which roughly matches what's self-reported on their website. So we were able to achieve some pretty great results here. On an A100 GPU, we were over 30 billion pairs per second, and on a H100 GPU, we were over 40 billion pairs per second. So we're in the range of 3 orders of magnitude faster than most of these implementations, and 2 orders of magnitude faster than ChemFP at this time. There are a few caveats to that. So it takes us a lot of compute to get up to saturation of the GPU to get to that throughput. On the right here, I'm showing basically like the speed up over RDKit as you increase the number of fingerprints in the n by n calculation. And so you really need 14,000 by 14,000 to max out the resources on the machine at this point. My benchmarks assume the data is GPU resident and in a form that's ready for it. We do have Morgan fingerprint generators that get it into that form. But not a general purpose. And we have utilities to pack NumPy torch vectors into that form. But if you need to do it, there will be some overhead. Another note is the ChemFP benchmark was from the free public version. There's also a paid version. I don't know if it has extra juice for this matrix. You quickly run into memory issues too. So this 16 by 16, 20 by 20 will even fit on an 80 gigabyte GPU. But if you have a smaller GPU, you'll run into memory issues quickly. And we will eventually run into memory issues quickly because with a dense similarity matrix, it grows as n squared. So on this H100 that I benchmarked on, I think it's somewhere around the 22 by 22 range where we'd start to fail. And then finally, a lot of these packages, ChemFP, FPSIM2, yeah, ChemFP, they have a lot of other functionality and some optimizations they can make. There's some cool things when you have a database that you're indexing into that you can sort it by bit counts and discard hits if you're looking for like a similarity greater than 0.8 or something like that. So there's a lot of optimizations, bells and whistles that this library does not have right now. I'm kind of hoping this would be more of the back end rather than us implementing, all the database stuff ourselves and memory management, but we'll see where it goes. I just wanted to point that out though. This is not a fully fledged lookup, software at this point, but I think our compute kernels are pretty good. Okay, the second topic is MMFF relaxation. MMFF is a force field that's shipped with the RDKit. I think it was implemented by Paolo. It's a typical MD-like force field. There's terms for bonds, angles, non-bonded, torsions. The minimization is driven by RDKit's in-house BFGS implementation in double precision, and that's what we ported to the GPU. For batches of molecules here, we use compressed arrays. So instead of taking the largest molecule and striding in your representation, we pack them back to back and have an index in to, so element 0 is here, element 1 is here. We do that for positions, we do that for metadata, we do that for force field parameters. The minimizer itself, a very simplified look at it, is you do a line search in the direction that you want to minimize, find out how far to move it. You move, you compute your new gradient at that point, and then you update the Hessian that's part of the BFGS, and then you exit if you've reached a minimizing criteria. This is a tricky one for GPUs for two reasons. One is that since we have to do this in batch, if any molecule is still running, the whole batch hasn't finished yet. And so that can lead to a tail effect where at the end, you've got empty molecules that are finished waiting for the last tricky case. The other thing is that this update, this check to exit the loop, we need to go back to the CPU for it. And so that is a synchronization operation where the GPU is not running. To complicate things further, the line search is its own loop where you try a new position, you compute that energy, and based on that energy, you back up or move forward until some criteria is made. So we have a double loop here with the same condition. So to try to tackle this, we do mini batching. You give us 1 million molecules, we'll do batches of like 200. That minimizes the tail effects to the best extent we can. And it lets us multi-thread so that when one of these batches is doing synchronization, the other one can run on the same GPU from a different thread and hide that latency. A quick note about the benchmarks here. Since we're multi-threading and RDKit can multi-thread, it's a little bit tough to come up with a perfect example for a benchmark. What we ended up with is running on one of our H100 DGX boxes. It's got 112 threads and 8 GPUs. So the benchmarks I'm going to show for this and the next section are RDKit with all those CPUs parallelized versus us with all those CPUs plus our GPUs on top. And so we have throughput in confirmers per second on the y-axis, and we're scanning over a subset of Kemble molecules. That's what these next two benchmarks are doing, separated by the total number of atoms. And so as you go to the right, both programs slow down because the bigger molecules take longer to minimize. That BFGS minimizer has an n-squared Hessian update step, so it definitely adds to the compute. If we show a speed up plot, we have better performance ratios on the larger molecules too. So the larger the molecules that you're minimizing, the better we can do ahead of the RDKit right now. This is the performance is a work in progress. I think we can probably push these ratios better. But in the middle range, typical of drug-like molecules, you're looking at 10 to 20 x speed up on that hardware. And I know not everybody has access to the most advanced machines, but we're not saturating the GPU all that well. And so if you have an A100 or a high-end desktop, you might see decent performance still. Okay, conformer generation. This is I'm not going to go over the whole algorithm because it was done better than me yesterday. This is just I'd like to mention that there's 3 different minimization steps right now. We're trying to get that down to 1 maybe. Each of those goes through this loop again. The in between and at the end are checks for stereochemical clashes, chiral violations, bad energies below a certain threshold. And so if any of these steps fail, the algorithm rewinds. And you have to do another iteration of the entire ETKDG algorithm or whichever variant of it you're using. This is an additional challenge for us because it's a third loop in our batch, which can be problematic. So you can have molecules that aren't finished the line search inner loop. You can have molecules that aren't finished the minimizer outer loop. And you can have molecules that are waiting for a failed molecule to redo the entire section. So we get around that by unrolling the outer loop and doing things independently in parallel. So whereas before, if molecule 1 finishes, it's got to wait for molecule 2, et cetera, and molecule 2 just runs again, and molecule 2 just runs again until it finally finishes. We just oversubscribe and throw a bunch of replicates at the problem. And that way, we do a bit of extra work. And so things that finished right away may have had some duplicates, but it lets us avoid this tail effect a little bit better. Our throughput and performance is similar to with MMFF relaxation, and that's because the minimizer dominates the runtime. So the trend is the same. Our performance isn't quite as good. So instead of getting up to 20x, we're up to 15x. There are a lot of caveats here. I have only implemented ETKDG with default parameters. I was listening to Greg talk yesterday about how people who do that are often mistaken. I was like, yep, that's me. The good news is we can implement this very quickly. It's just force field terms, and we're ready to. We'll be able to quickly support KDG and DG in the various variants. But very few of the non-default options work at this point. If you want them, let us know, and we'll prioritize working on them. Okay, so our release 1.0 is out. We have a current list of priorities, but please try it out, find bugs for us, and tell us what your pain points are, and we can work on them. This is kind of an early version of the software, so expect bugs, expect sharp ends, and we'll iterate as fast as we can. So I only have a couple minutes left, so this is going to be very quick. Wanted to talk about some of the, we've submitted several PRs, most of them in October of last year. So if you have 2503 in RDKit, you should see these speedups. For Morgan fingerprinting, we did some deduplication of comparisons and a couple reuses of data to get between a 60 and 100% speed up on typical radii, 2 or 3 for Morgan fingerprinting. We helped out with smiles parsing, particularly of large molecules. So you'll see no effect on small molecules, but if you have over 100 atoms in your molecules, we worked on a hotspot there in the CYP labeling code. My colleague Eva rewrote the Butina clustering algorithm to use NumPy under the hood, which gives a 2 or 3x speed up naively, but we also added the ability to put in a distance matrix, such as from Tanimoto similarity. And in that case, you can get 10x speed ups because you don't need to recompute things, and you can do it in batch. Last thing is my colleague Nia is working on some changes to the core data structures. There's a lot of memory allocations in the boost graph that RDKit moles are made up. Each atom has its allocation, each bond has its allocation. And so bouncing around between them for iterating over molecules and properties can be very slow because they're not in the same memory location. Our work in progress condenses these into compressed arrays. So if you want to loop over atom properties, you're getting a lot more cache hits because bringing in atom 0 also brings in atom 1 and so on. This is a draft. There's a couple failing tests. There's some work that needs to be done. But if you're interested, check out PR 8591. All right, that's all I had. I want to say thanks again, and I really want, RDKit's a great code base to work on. I've worked with a lot of scientific software over the years. I think this is the best tested code base. So all the mistakes that I made and broke things immediately came back to me in the unit test, which was really great to work with. Thank you.
Let me have the mic briefly before we move to questions. So before we move to questions, I want to answer perhaps preemptively 1 or 2 questions. When there was an announcement on LinkedIn about this yesterday or this morning or something, and a couple of questions about that came up. The first one, and kind of a logical one, is when this lands in the RDKit. And the answer is never. So now let me explain what I just said. This code uses a GPU, and GPUs are great, but they don't exist on every platform that the RDKit supports, and they don't exist on every machine they support. And their supporting GPU code is very difficult, and I and many of the maintainers don't know how to do that. So I've been talking to the team at NVIDIA for a couple of years about these changes, and the solution we arrived at to solve this is there's the open source NVMol kit that they're doing. That's going to use the same version of the RDKit that you're using. They can then support the GPU code and take care of all of that. We can support the RDKit code and take care of all of that. And in the end, if you want to use the CUDA code, there's 1 extra thing to install. Okay, so this will not end up in the RDKit. That's okay with both sides. We're all happy with that. That's planned. That was the most important ones. I just wanted to make sure that everybody got that before the question came up. This has also not been something where NVIDIA just appeared with a bunch of stuff without talking to anybody. We've been talking about this for a long time. And as you've seen, there's also been a lot of contributions to the core RDKit to improve performance. So this has been a great collaboration, akin to some of the collaborations with some of the other commercial software companies that we've had so far. So just from my side, this has been great, and I'm really happy about this. Hopefully that fends off that particular question. And now I'll give it back to you. And thank you. People can ask questions.
Yeah, the comments is, the second comment is the possibility of pre-allocating using JMalloc and using a mempool to then allocate your molecules. And that's, yeah, that's definitely interesting. It could work. The smiles, yeah, sure. Yeah. The first reaction I would have to that is that if you're still mallocing, your atom data, your bond data, it's probably less optimal if you're, say, adding an atom and then a bond, and then that data is still not contiguous even within the memory block. But the reducing the number of allocations and getting everything compressed in some order, definitely, yeah, I could believe that would be a huge speed up.
I don't have anything against Wikipedia pictures. But in terms of the package, I see that because the difference of the compilation, my question is more, is it able to make that framework? So your Mac, because the Mac you have the CPU and GPU that are for it. And so you don't have to for all of the transmission system. And I guess for the optimization problem, it is much faster.
So I think if I got that all, you said it was about Max that you're talking about with the combined CPU GPU, and that how that might be faster. I'm not actually sure. I live in the Linux world pretty much exclusively, and that is a gap. I am sure that we have people working on making those systems faster. They can run on, well, versus do they run NVIDIA? I don't know. I shouldn't comment on that because I'm not actually sure. Good question. So the question is, if you don't have one of the flagship GPUs, what can you expect and what do you need? It depends on the module. For the similarity calculations, it should be just a ratio of what. So for a gaming GPU or workstation one, you can look up how many flops it has. That ratio should hold pretty well for all the modern ones. The issue with the similarity you'll run into is the memory. So if you've got like just a 10 gig GPU, then you can't necessarily max out like with matrices that size. But on the other hand, you'll max out the performance of the GPU quicker. Yeah, so you don't have to get to 15K by 15K to max out a smaller GPU. The minimizer stuff might be a little bit worse, but not because the GPU is smaller or because of bandwidth, but because the non-data center GPUs have worse 64-bit floating point performance. It's by 30x. Now, we're not saturating the GPUs all that well, and so you might not see a huge decrease, but if there was going to be a big hit, It's not from smaller GPU or bigger GPU. It's going from data center GPU down to like a workstation or a gaming GPU, because just by nature, the floating point performance ratios are different. So the question is, where are we CPU limited? Were we? Yes. On Morgan fingerprinting. So I didn't include this. We are completely CPU bottlenecked on Morgan fingerprinting. The GPU is sitting idle a lot of the time. We're still getting decent performance ratios, like 4 or 5x. But it's the invariants that you need to pre-compute from RDKit to put them on the GPU to compute the fingerprints. We're multi-threading, so when you double the threads, you double the RDKit performance, and you almost double our performance. It's like 98% up to 8 threads, but we're still CPU bound here. An early prototype of those core changes that I talked about, a long time ago, I incorporated them into one of our dev branches, and we got rid of that bottleneck. So that's one anecdotal data point towards the condensed representation on the CPU helping things out.